presentations. First up, we have Jianyu Jiang from the University of Hong Kong telling us about Kakute.
Okay. Hello everyone, I am Jiang from the University of Hong Kong. Today I will present Kakute. It is a system that can provide big data security and reliability. This work is done with my colleagues Shixiong, Danish, Yuexuan, Feng, Zhaoquan, and our supervisor He Mingcui. Nowadays, companies use big data frameworks such as Spark to process data records. In practice, the company may allow third-party analysts to submit self-defined queries, such as data mining tasks. They can be Spark tasks that contain math and reduce functions. However, these incur privacy concerns, as these third-party analysts may be malicious and try to steal user-sensitive data. For example, there's a medical record here, and it consists usernames, disease ID, and a rating from 0 to 10 of the severity of the disease. Users want to keep their personal information secret, so the name of the record are sensitive and are not allowed to be known by the third parties. And analysts submit a query to sum up the severity of all records. In the map function, the first and third fields are extracted, and in the reduce phase, the severity is summed up. But if the analyst write a query that writes sensitive data, such as Alex, directly through I/O channel in the reduce query, sensitive data may be leaked. Originally, the reduce function should just return the 8 here to the output, but analysts may also write sensitive user data to the output directly and collect them. So it also results in sensitive data leakage. So how can we tackle these problems? So information flow checking is a powerful technique for preventing such kind of data leakage. The idea of this technique is to attach security tags to sensitive data and prevent data output with these tags. It has been applied in smartphones, web services, and server programs. For example, TinkJoy, it is a famous IFT system in Android, uses IFT to protect sensitive user data, such as GPS and contact information from leaking out of the cell phone. Here, I use the TinkJoy to show how IFT works. We have an application here, and it takes GPS data as input, so every variables, such as C, D, computed from the GPS are sensitive. Here, each sensitive variable is tagged with an integer label 1, and insensitive data is tagged with 0. If the application sends the sensitive data D to the outside world directly, IFT will detect this label 1 and know that this data is sensitive, so the data output is prohibited. IFT is such a powerful tool for such mandatory access control. However, as far as we know, there's no IFT system for big data processing framework. We have found two major challenges when applying IFT in big data. First is the performance challenges. We ran a recent IFT system Phosphor in Spark with a WorkCount program, and we found that the performance overhead is more than 100 times compared with native Spark execution. For another IFT system that supports web programs, it incurs 3 to 5 times computation overhead. We found that the key reason is that tag propagation in data-intensive computation are too slow. The second challenge is to completely check tags across machines. In big data framework, data records are partitioned into multiple parts and are processed in parallel. So there will be data record exchanges across machines. This exchange process is called shuffle. However, most IFT systems ignore the information flow across machines. Therefore, security tags may be lost, causing severe data leakages. We present Kakute, And as far as we know, it is the first IoT system for big data framework. Kakute is a fine-grained information flow checking system. It can check different sensitive levels for various fields in data records. We implemented Kakute and integrated with Spark. Kakute is transparent. It can run unmodified Spark queries. Third-party analysts does not need to know anything about the Kakute, and they will submit tasks like what they do previously. On average, Kakute has only 32% performance overhead on various big data programs and datasets compared with the native Spark execution. This is achieved with the help of our two fast propagation techniques. They are called reference propagation and tag cache. It is possible to run Kakute in production system with this low overhead. I will present these two techniques in the next few slides. Kakute also provides easy-to-use APIs for tackling various security threats. We have implemented several security and reliability checkers, including information flow control, data provenance, and debugging. It can be used for other applications too. The rest of my talk is as follows. I'll first introduce the system architecture of Kakute and show how IFT works. Then I will address our solutions to the true challenge I mentioned before. And last, I will show our evaluation results. First, let's start with the system architecture of Kakute. We have two machines running Kakute here. Data record first go through a map operation and then shuffles so that records with the same key are in the same partitions. And last, the program reduces on the map results and sends to output. Kakute only performs IFT on the self-defined query marked as the orange boxes, not the entire Spark framework. This can reduce performance overhead greatly. Here we have the data medical record with patient name sensitive and tagged with the security level 1. These records are partitioned into two parts and processed in different machines, and tags are automatically attached based on the user policies set by Kakute. They first go through a map operation, and then there's a shuffle process that transfers the ALEX3 record from machine 2 to machine 1. In the reduce phase, the reduce function sums up the severity and send it to the final output. In both map and reduce, tags are propagated from the input to output. In the shuffle process, tags are propagated from one machine to another. If the reduced queries are malicious and sensitive data is included in the final output, the Kakute will throw an exception to abort the query and prevent the sensitive data leakage. Then let's show how Kakute do the IFT. Kakute modifies Java bytecode for information flow checking, and it intercepts in each bytecode instructions for tag propagation and storages. We use the Java agent API to intercept the class loading process to run Kakute transparently. For example, we have the data record here, and the map function passes the record, and the reduce function sums up the value and with the same key. And in the map function, the value is directly assigned, so the tag is also transferred directly. In the reduce phase, it needs to combine two tags. So Kakute do a simple OR operations to keep the highest security tags. Here, I will not go through the tag propagation policies, and as it is similar to TinkJoy and other IFT systems. Then I will introduce the two techniques for fast tag propagations. When there's more records, the output are similar. We propose a reference propagation technique. This technique does the actual computations on records and propagations and propagates tag in an on-demand manner. For example, if the reduced query only needs to output the severity 8 associated the key Alex, then Kakute only does the computation and tag propagation only on this upper half. We propose another technique called tag sharing. Instead of allocating tags for every field in every records, we observe that many records or fields often share the same security tags. Here, D5 share the tag 0, and therefore, Kakute makes the tag in the caption circle share the same tags at one time, which reduces memory and network bandwidth consumption. I will show how this technique can reduce network bandwidth consumption in the next few slides. If you are interested in the implementation detail, you can also read our papers. Then I will introduce our solution for the cross-machine tag propagation. Let's first see why it is so important. Suppose we have the map results previously, and then the result is shuffled across machine. Then Alex3 will be transferred from machine 2 to machine 1. If we does not have cross-machine propagation, then the tag for Alex3 will be 00 instead of 10. So if an malicious analyst tries to write sensitive data Alex3 in the reduced phase, he can actually succeed and causing the sensitive data leakage. So how can we propagate tag across machines? To completely capture the tag across machines, we intercept the shuffle process of Spark for cross-machine propagation. Here, we need to transfer the Alex32 from machine 2 to machine 1. When the record goes through the shuffle module, Kakute automatically expand with its tag as a new tuple. Here, 100 is the tag for Alex32. Then this record will be transferred from machine 2 to machine 1. This process also benefits from the tag sharing techniques, as we mentioned above. Here, the multiple fields of this record share the same tag 0, and Kakute will only transfer one copy of this tag, so it can reduce network traffic on propagating tags. Now, the expanded record is transferred to machine 1, and the record shrinks and the tag is attached when going through the shuffle module again. After that, the shuffle process will finish, and the tags are now propagating across machines. Kakute also addresses other technical challenges in our implementations. First, it supports per record tags. Kakute can attach unique tags for each data record for security and reliability tasks. Second, Kakute can support some implicit flows such as emitting and constant from a sensitive record. Third, Kakute can automatically add tags to record when loading them into Spark. Finally, Kakute provides easy-to-use API for building applications for various security and reliability tasks. We have built 4 applications, including data provenance, information flow control, debugging, and performance tuning. Then I will show our evaluation results. Our evaluations were done on 9 Dell servers with 24 core CPUs and 40 GB network cards. Our evaluation answers the following questions. First, can Kakute defend against data leakage? Second, what is Kakute's performance overhead compared with native Spark execution? Third, how is Kakute's performance overhead when scaling to large data sets? Our evaluation is done on diverse programs, including computation-intensive programs and network-intensive programs. For datasets, we use practical graph datasets such as Twitter social network with up to billions of edges. We use, for the text processing, dataset, we use Wikipedia, which is up to 300 gigabytes. All the datasets are comparable with relevant systems such as Big Debug and Titan. Let's see how Kakute prevents sensitive data leakage. We ran a malicious query shows in previous papers on medical records. Both the queries should just sum up the severity, but in the first malicious queries, it writes user names directly into the remote servers. In the second query, it writes patient name directly to the output and collect it. For both cases, Kakute detects the sensitive text and through a one-time error, and then the query will abort to prevent leakage of sensitive data. It also returns the query and the sensitive record that may be leaked to Kakute. We then shows the performance overhead of Kakute. The x-axis is the dataset we tested, and is the program we tested, and the y-axis is the performance overhead of Kakute. Here 100% means there's no performance overhead, and it runs as far as native Sparks. For all applications, Kakute has on average about 32% overhead. The overhead is small compared with other IT systems, which usually incur several times overhead. Here shows the scalability of Kakute running various sizes of datasets. The x-axis is the dataset size, and the y-axis is the computation overhead of Kakute. For all programs and datasets, Kakute can scale up to billions of records and several hundred gigabytes of dataset. Next, we need to see the scalability of work graph. The performance overhead does not increase much with the increasing of dataset size. It has a performance overhead drop when increasing the dataset size at the beginning. This is because the time for running Spark is too short for computations when the dataset is too small. So the initialization cost of information for checking takes a large portion for computation. When the dataset size is large, Kakute's overhead is small. It only occurs like 10% performance overhead. So to conclude, we present Kakute, a precise and fine-grained information for checking system. It has moderate performance overhead. We have also built several applications such as data pullings and information flow control using Kakute's API. Just like other IT systems such as Titan, such as Tengjoy, Kakute has broad applications for improving big data security in the future. For example, we can combine it with the differential privacy and adds noise to only the sensitive fields. And we can also use it to verify data flow automatically. All the source code of Kakute are publicly available in the GitHub. Thank you all, and I would like to take questions.
Are there any questions? Please. How does Kakute handle aggregations of information? So let's say I concatenate strings in my Spark program.
Do you mean in the reduce phase when there's two records combining? You mean how to handle the propagated data flow?
I may misunderstand. You say that I don't have to modify my Spark source code?
Yes.
In this, so let's say I concatenate
Yeah.
fields in a like a reduce by key in Spark or something.
Okay. Yeah. I get your.
How did the tags work?
Okay. So the Kakute will it use the Java API called agent. It intercepts the class loading process it also modifies the Java bytecode. It will intercept the tag propagation instruction for each instruction. So if there's a addition operations, then there will be also a tag propagation instruction. So when you maybe in the reduce phase, you add up two variables, and the tag will be propagated correspondingly.
Okay, and I guess my question is you have multiple tags for the input of the reduce
Yes.
to produce a single output.
Yeah.
So what's the tag of the output?
It is the single OR of the original text for the information flow control case.
Got it. Okay. Thank you.
Yeah.
Any other questions? Please. You showed us that bar graph, I guess it was slide 15.
15?
Yeah.
Let's see.
That one. No, sorry, so one, 16?
16?
16.
Six.
Other way, 16.
Okay.
Yeah, that one. I didn't understand why you have such big differences depending on all these operations. So what does it change so that you have 1% overhead on the word graph and, I don't know, 100% overhead medical sort?
You mean the performance overhead difference?
Yeah.
The performance overhead difference mainly come from maybe two parts. It depends on what the programs do. Here we have some, maybe if it is computation intensive, so it has to propagate many tags, so the performance overhead will be high. And for some, maybe for some shuffle intensive applications, so the performance overhead mainly comes from propagate tag from one machine to another. So it depends on the.
Okay, it depends on the operation.
Yes.
That you do. Okay, so that means that maybe you can use Qt for a specific subset of these operations in which it was predefined. Maybe for the medical source, you need to have, I don't know, another technique maybe. Because if I always do that kind of operation, I'm likely not going to use these because I cannot handle 100% overhead on all operations.
Yeah.
The question is, do you have other techniques maybe that can replace Qt for such kind of operation?
Yeah, I think that's a good idea, but we have not considered replacing the operations for in our implementation.